Hello, in this video I'm going to solve the following problem for you. The subject is topology and the topic is topological spaces. Let X be an infinite set. Show that tau equals to the set of all subsets U of X such that either U is the empty set or X minus U is finite is a topology on X, which is called the finite complement topology. Pause the video at this point and give it a try. Okay, in order to show that tau is a topology, I need to show that axioms of a topology is satisfied. Of course, here it is mentioned that X is an infinite set. It doesn't mean that if X is a finite set, this is going to be wrong. Even if X is a finite set, this is indeed a topology on X. In that case, this is the discrete topology. Why is that? Because if X itself is finite, no matter what subset of X you choose, X minus that subset is always finite because X itself is finite. So it means that all subsets of the set X will be included in tau, and that is exactly the definition of the discrete topology. In that case, the topology becomes the power set of X, and you know that the power set is the biggest topology that you can impose on a set. Okay, so that is why in the problem we have emphasized that X is an infinite set, because for the case that X is finite, this topology turns out to be the discrete topology. Okay, but of course the solution that I present here, it doesn't assume anything about cardinality of the set X itself. The first thing that I have to guarantee is that the empty set is included in tau. Okay, so the empty set is of course the subset of any set including the set X given in this problem. So this is always guaranteed. And we know that the empty set is of course equal to itself. So this is true. So it means this part is guaranteed, yes? Because in order for a subset to be able to go into T, to be a member of tau, it should satisfy this condition. It means that it should be a subset of X, and it should satisfy either this condition or that condition. If that is the case, then that subset will be allowed to be a member of the tau. Okay, the empty set is a subset of X, and the empty set is equal to the empty set. So both of these conditions are actually fulfilled, so it guarantees that yes, empty set is indeed an element of tau. On the other hand, you know that X is also a subset of X itself, and you also know that X minus X is the empty set, is finite, yes? Okay, so X is a subset of X, so this condition is met by X, and X minus X is the empty set which is finite, so this means that yes, X also belongs to tau. Okay, so the empty set belongs to tau, X itself belongs to tau, so these conditions are met. For the second part, I would say that let U1 and U2 both belong to tau. We show that U1 intersect U2 belongs to tau. Okay? So, if U1 intersect U2 is the empty set, because this is one possibility for U1 and U2, then we are done. Yes, because we already showed that the empty set belongs to tau, and if this is going to be the empty set, it already belongs to tau. So let us assume that U1 intersect U2 is not the empty set, and try to prove that U1 intersect U2 belongs to tau. Okay, when you say that U1 intersect U2 is not the empty set, I am allowed to conclude neither one of them is the empty, because if at least one of them is empty, the intersection will be also empty. So it means that U1 is not empty and U2 is not empty. Okay? Okay, U1 is not empty, but we know that U1, it belongs to tau. So U1 belongs to tau and it is not empty. So this means that x minus U1 is finite. Yes? And now for the same reason, U2 is not empty, but we know U2 belongs to tau, so this means that x minus U2 is finite. Yes? Okay, and we know that if two sets are finite, the union of those two sets, meaning x minus U1 union x minus U2, is finite. Okay, but from De Morgan's law in set theory, this set can be written as x minus U1 intersect U2. Okay, this set that you see here by De Morgan's law can be written in this form. If this set is finite, this means this one is also finite because they are equal. Okay, but of course you know that U1 and U2 are subsets of X, and therefore the intersection will also be a subset of X, and we know that X minus U1 intersect U2 is finite, so this means that yes, U1 intersect U2 belongs to tau. Okay, so what I'm saying is that if U1 intersect U2 is the empty set, this condition is met, and U1 intersect U2 belongs to tau, we are done. If U1 intersect U2 is not the empty set, then according to this reasoning, again U1 intersect U2 will belong to tau. So in both conditions we are done. Okay, now for the last part, I would say that let U alpha belongs to an index set, let me call that index set I, be a collection of elements, or if you want sets, in tau. We show that the union belongs to tau. This is what we want to show. Of course, if the index set is the empty set, then what happens? We know that by set theory, what you learned in set theory, this becomes the empty set, and empty set belongs to tau, we are done. Okay, but let us assume that the index set is not empty. If the index set is not empty, this is still possible that the union of these alphas become empty, yes? And that is the case that if all of them are empty. Okay, so if the index set itself is empty, the union of the collection becomes empty, and we are done. If the index set is not empty, but the union is empty, meaning that all of these U alphas are empty, then of course again this belongs to tau, and we are done. So we considered the case that I is not empty, and of course U alpha is also not empty, yes? In this case, we want to show that this is still the case that the union belongs to tau. Okay, when you say that I is not empty and the union of U alpha belongs to I is also not empty, I can conclude that there exists an index B in the index set I so that U beta is not empty. Okay, this is guaranteed by these two conditions. Okay, U beta is not empty, but I know that U beta, being an element of this collection, is in tau. So this means that x minus U beta is finite. Okay, now let us consider x minus the union of U alpha belongs to I. According to De Morgan's law, I can write this as the intersection of x minus U alpha belongs to I. Okay, But be careful, U, x minus U beta, is one of the sets of this collection. So, and this is the intersection of all of them. So definitely this becomes a subset of x minus U beta as a particular element of this collection. Now what happens? So x minus the union U alpha, alpha belongs to I, is a subset of x minus U beta. But this one is finite, as you see here. So this will imply that x minus the union U alpha, alpha belongs to I, is finite. Okay, and of course it is clear that if all U alphas are subsets of X, their union is also a subset of X. So this means that this set that you see here is a subset of X on the one hand. On the other hand, its complement, X minus the set itself, is finite. So this means that the union U alpha, alpha belongs to I, also belongs to tau. Okay, and we are done. Okay, so these are the axioms of a set, of a collection of sets to be a topology. I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.